Alright, in this video we're going to be talking about L'Hopital's rule. And this is going to be a rule that we can use to help us evaluate tricky limits. Okay? But I'm going to start with kind of a motivating example. We've dealt with limits in this class already, but the limit that I've got on screen right now, the limit as x approaches 0 of 1 minus e to the 2x divided by x. This is not the type of limit that we actually know how to solve yet. You can try to do all sorts of algebraic things with it, but you're not going to get a satisfying answer out of it. So what I'm going to do, I'm going to show you the graph of f of x equals 1 minus e to the 2x divided by x. All right, so there you go. So there's the graph of f of x. And I'm realizing I haven't typed it in right. Alright, there we go, that's more like it. So that's f of x equals 1 minus e to the 2x divided by x. And we can see if we're looking at the graph that the limit as x approaches 0 of this function definitely exists. But we also know that if we were to plug in x equals 0, we'd get 1 minus 1 divided by 0, and well, division by 0 at all is not allowed, but I'm just going to let it get really close and see what happens. Okay, it's undefined, but it looks like it's getting really close to negative 2. It looks like it's passing through that point, so that must mean that there's a hole in the graph at x equals 0, and it looks like the limit should be negative 2, so let's see if we can make that happen. And that's where L'Hopital's rule comes in. So we're going to need this in order to compute that limit. Okay, so indeterminate forms, that's maybe a vocabulary word you've not seen before. Okay, something like 0 divided by 2, okay, that's always going to be 0. 3 divided by 0, that's always going to not exist, right? Those are determined, right? An indeterminate form is the type of thing that can come back all sorts of ways. Okay, a fraction that's going towards 0 in the numerator and the denominator, as you'll see in this lesson, because that's kind of the primary focus in AP Calculus, that can come back with all sorts of results. It can come back 0, it can come back 1, it can come back 3 halves, it can come back infinity, and all sorts of things. And actually in AP Calculus, we're only interested in the first two. Okay, but I'm going to tell you, I typed it out for you so you can see those are the indeterminate forms. We are not going to write those at all. What I'm saying this year is that we are totally allergic to these fractions. We cannot be writing these down in our own handwriting ever for any reason. Okay? And the reason why I'm, kind of gone so psychotic about this is I am a grader for AP Calculus, and I've graded enough of these, and I have seen so many responses that get the correct answer but are not getting the justification point, that I just really want to impress on you the urgency of not ever writing down 0 over 0. Okay, and in my class, that's just going to be the type of thing we're not going to do at all. And looking at the theorem, the actual rule for L'Hopital's rule, you can see, where the logic is, and you're going to see what we're going to do instead. Okay, so what the theorem says is that if we're getting 0 on top and bottom, or infinity on top and bottom, both, then the limit that we're looking at is actually equal to the limit of the ratio of the derivative of top and bottom. Okay, so what we're going to do, we're going to take the derivative of the top, the derivative of the bottom separately, no quotient rule. And we're going to check the limit of that. And I've always found this a pretty surprising result. But kind of the conditions of the theorem are the hint to how we're going to need to justify our answer. So I'm seeing the if statement. If these limits are both 0, or if these limits are both infinity. And this does mean that we're going to need to evaluate the limits of the numerator and denominator of these fractions separately. Okay, so I'm going to show you what I mean by going back to that original motivating example. All right, if I look at this fraction, as x approaches 0, both the numerator and denominator are also approaching 0. So I'm going to point that out. Okay, so that'll be, the limit as x approaches 0 of the numerator. That's going to equal 0, and then I'm going to also point out that the limit as x approaches 0 of the denominator is equal to 0, and then that's going to justify my use of L'Hopital's rule. Okay, I'm going to come in, and to the right of that, I'm going to rewrite my limit, and that will be the limit as x approaches 0. I take the derivative of the numerator. I'm going to get 0 minus 2e to the 2x, and that's where that negative 2 is going to come in. Divide by the derivative of x, which is 1, and then reevaluate. If I'm not seeing both the numerator and denominator going to 0 or infinity, I don't need to use L'Hopital's rule, right? The numerator is approaching negative 2, the denominator is staying constantly 1, so this limit is going to equal negative 2. And that's how we do L'Hopital's rule. So let's do it again. So this is kind of a classic limit from Calculus 1. You know, any good Calculus 1 class is going to tell you about the limit as x approaches 0, sine x over x. I may have discussed this with you at the beginning of the school year, but probably not in too much depth, because I knew that today would come. We would talk about L'Hopital's rule, and we're kind of in a hurry in the high school class. So this one, if you think about x approaching 0, sine x is going to be approaching sine of 0, which is 0, and the denominator is clearly going to be approaching 0, so I'm going to show those separately. So I'm going to say the limit of sine x as x approaches 0, that's 0, and the limit of x as x approaches 0 is also 0, so I'm going to apply L'Hopital's rule. And so that's going to be involving me taking a limit, still as x approaches 0, but of the ratio of the derivatives, like the derivative of sine x and the derivative of x. So I'm going to take the derivative of sine x and get cosine x, and I'll take the derivative of x and get 1, and then I'll kind of like reevaluate and think about, okay, what's going to happen here? When I plug in x equals 0, okay, I'm going to get 1 in the numerator. I already know I'm not going to be doing L'Hopital's rule because I see 1 in the denominator, so I'm going to just say, okay, well, this is cosine 0 divided by 1, which is just going to be 1. I want to do one more example for you before I move on to the infinity-related ones. So as t approaches 0, we've got this e to the t minus 1 minus t divided by t squared. And it's like, uh-oh, the denominator is going towards 0. This is probably going to be L'Hopital's rule. I think about the numerator, I'm going to have 1 minus 1 is 0, minus a 0, yep, and we're going to have 0 and 0. Okay, so I'm going to evaluate the limits separately. I'm going to say the limit of the numerator is 0, the limit of the denominator is 0, so I'm going to apply L'Hopital's rule. And so I'm taking the derivative of the top, that's the derivative of e to the t is e to the t minus 0 minus 1, okay, divided by the derivative of t squared, that's going to be 2t, and then I'm going to kind of reevaluate. I'm thinking about the denominator, it's still going to 0, and it's like, oh no. But I think about the numerator, and it's also going to 0. And I mean, I don't think I've mentioned it yet in this video, but I think you know what I'm about to do. I'm going to tell you that, you know, if you keep getting 0 over 0, then you can keep using L'Hopital's rule. So we're just going to apply it again, and we're going to justify our use of it the second time, even though I do believe that, you know, like on the free response section of the AP Calculus exam, which is where we really need to be careful about where we're justifying our answers, they would probably not ask for a 2-iteration L'Hopital rule, you know, problem, just because there's not a whole lot of value added. Okay, just, if you know you can do it a second time, then that's exactly the type of thing you can test in multiple choice. So the denominator, 2t, that's also approaching 0, so okay, I'm going to have to do it again. So I'm going to take the derivative of e to the t minus 1, that'll just be e to the t, and I'll take the derivative of 2t, and I'll get 2, and this is good news, because I see that 2 down there, I know at least I'm not going to have to do L'Hopital's rule another time, if I'm kind of running out of room here. So I'm going to think about the numerator, I'm approaching e to the 0, that's going to be 1, the 2 is going to stay constant, this limit's going to be a half. Okay, so now the ones with the infinities. So as x approaches infinity, we have x squared divided by e to the x. Okay. What I would say about this one is you already know the answer to this one. We've covered this in this class. E to the x grows faster than any polynomial. It's in the denominator, so as x approaches infinity, this thing approaches 0. And it does not require justification. But if in August, or whenever you started this course, you were sitting there thinking like, I don't know about that, dude. I don't know if I have really good reason to believe you that either x grows faster than any polynomial. Maybe L'Hopital's rule would be a reason to believe me. So I'm looking at the numerator and denominator as x approaches infinity. Both of these are growing without bounds. So I'm going to say, okay, the limit of the numerator is infinity, the limit of the denominator is infinity, so this justifies my use of L'Hopital's rule. Okay, so I'm going to say I'm taking the derivative of x squared and the derivative of e to the x. I'm going to reevaluate. Okay, same story. So maybe I need to use L'Hopital's rule again. So it's like, okay, the limit of 2x is infinity, the limit of e to the x is infinity. I'm going to do it again, take the derivative of 2x, take the derivative of e to the x, you know these derivative rules. Okay, and here we have got ourselves a limit of a fraction whose numerator is staying constant and whose denominator is growing without bound. And that's a situation we looked at a lot last year in my pre-calculus class. This is precisely the type of fraction that approaches 0 as the input approaches infinity. So I'm just going to say this equals 0. Okay, and what I will, once again reiterate that a person could just respond only with the writing in red and be correct and, not need to justify themselves any further. But something that was brought up today in my class, which I really liked, was somebody was like, you could just keep going and then the numerator would equal 0 and the denominator would be e to the x. I was like, yeah, that makes a lot of sense. But that is actually fool's gold, because remember that we can only apply L'Hopital's rule when both the numerator and denominator are approaching either both 0 or both infinity, right? Okay, so that's an important distinction. Another infinity-related example I've got is this natural log x divided by the square root of x. Okay, so again, in August, I told you that, log grows slower than any power of x. Okay, so the power is growing faster, it's in the denominator, therefore the thing's going towards 0. So you could say that, but again, if you had any doubts about that, maybe you think about it in terms of L'Hopital's rule. The numerator is going towards infinity, the denominator is going towards infinity. Okay, we're going to take the limit of the ratio of the derivatives. The derivative of log x is 1 over x, and the derivative of square root x, that's going to be 1/2 x to the negative 1/2. I'm going to kind of rearrange and simplify this. The 1/2 in the denominator would become a 2 in the numerator, 1 over x in the numerator. Okay, sends the x to the denominator. All that stuff moving around, I'm going to end up with 2 square root of x divided by x. But I can simplify that because I know that x is square root x times square root x, so I can kind of mentally cancel one of those off and say, okay, I'm left with x approaching infinity, 2 divided by the square root of x. And this is a fraction where the numerator is staying constant and the denominator is growing without bound. That is exactly the type of thing that approaches 0. And here's one from a somewhat recent free response. That's from the 2023 Calculus AB exam. So if f of 2 equals 1, find the value of this limit or show that it does not exist and justify your answer. All right, so what we're going to do is we're going to kind of look at this, think about the denominator. Okay, 4 minus 10 plus 6. Oh yeah, that's going to be going towards 0. Probably going to be L'Hopital's rule. They're telling me f of 2 equals 1, so that would be 6 times 1 minus 3 times 2. Yeah, okay, I'm getting 0 and 0. So I'm going to write those out. I'm going to say, all right, the limit of the numerator is 6 times 1 minus 3 times 2, which is 0. Okay, the limit of the denominator is 4 minus 10 plus 6, which is 0. And so I'm going to use L'Hopital's rule. Okay, so I'm going to take the limit as x approaches 2, and I'm going to take the derivative of the top and the bottom separately. So the derivative of the top would be 6f prime of x minus 3. And the derivative of the bottom would be 2x minus 5. Right, so I'm going to kind of set it up, plug in. It's going to be 6 times f prime of 2, or the limit of f prime as x approaches 2, but okay, we can see that's going to be 0. Okay, so 6 times 0 minus 3 divided by 2 times 2 minus 5, and that's going to be a safe place for us to stop, right? In AP Calculus on the free response, we don't have to simplify our answer. We'll just go ahead and stop right there. Next section of the notes is titled L'Hopital's rule isn't always the way to go, which is definitely kind of what I want to wrap up by talking about. But I thought I'd just kind of include these 3 examples also. I definitely went over ones like these in all of my classes because, they're important for us to not forget about as well, even if they're probably the types of ones that we could have done last year in pre-calculus. So as x approaches 1, x plus 1 over x minus 1. I'm also going to show you that I think if we show our work kind of the same way we were with L'Hopital's rule, that could maybe take some of the worry out. Just like if we're dealing with the limit of a fraction, we just do this every time and it's really not that bad. So as x approaches 1, x plus 1 is approaching 2. And as x approaches 1, x minus 1 is approaching 0. So the numerator is going towards 2, the denominator is going towards 0. We're trying to divide by 0. That still doesn't work. Okay, we've seen that the indeterminate form 0 over 0 sometimes has a more interesting limit. But still the value doesn't exist, and this limit is just not going to exist because we're getting closer to 2 over 0, so we're just going to say dne. For the one in the middle, we're going to do the same thing. We're going to say as x approaches 2, the numerator approaches 3, and the denominator approaches 1, and we can divide 3 by 1. It's no big deal. That's 3 over 1. That's 3. Okay, so we got that. Okay, not that big of a deal to write it out. Okay, and then for the one on the far right, okay, as x approaches -1, the numerator is approaching 0, the denominator is going towards -2. We can divide 0 by -2. That's not a problem. 0 divided by a non-zero number is going to equal 0. So I'm just going to display my answer there, and there we go. I feel like I've covered that situation. Okay, well, this one was from 2019. And that was not a year that I graded free response, but I will tell you I have graded one like this before, like the fake L'Hopital rule question. And it must have been on a different version of an exam, I think more recently. And a lot of responses will kind of lead off with taking the derivative of the top and the bottom, and you cannot be doing that, right? Because of ones like this. If you look at the top, okay, it's going to approach 10 to the first is 10 minus 3 times f prime of 1. Okay, well, I am going to need to figure out f prime of 1. Okay, right there, the slope, that's going to be 2. All right, so this is approaching 10 minus 3 times 2 divided by f of 1 equals 1 minus the arc whose tangent is 1. Okay, and we're going to need to figure that out, at least in my class. So, thinking about the most obvious place on the unit circle where tangent would be 1 would be right here, where sine and cosine are equal. We've got that 45, 45, 90 triangle. That is theta equals pi over 4. So this is equal to, 10 minus 6 over 1 minus pi over 4. That was all we did was plug in, kind of like that one I just showed you on the slide before. But if the numerator and denominator are not both going to 0 or both going to infinity, we can't use L'Hopital's rule. And I think that's actually where I'm going to leave it for this video. I had one more down below, but that was kind of a, just a trick example that I went ahead and put in my homework as well, just for fun. And, so if you want to see me doing that, you can go check out the homework video. So that's all for this one. Thanks for watching.